Laboratory activity 3 is on measuring matter, and as you've been learning in your lectures, matter is defined as anything that takes up space and has mass. Mass is basically the stuff that something is made out of, the protons, neutrons, and electrons. When we think of space, we just think of volume. Now, since matter is defined as something that takes up space or has volume and has mass, if we knew the ratio of the amount of mass per unit volume for a type of matter, that would allow us to compare it with other types of matter. And we call this quantitative description of matter. Quantitative meaning there's a numerical value, a number that we can apply to it. We call that density. We can think of density as a quantitative measure of how much space a given mass occupies, or we can also think about it as the mass per unit volume. And that's the way that scientists have decided to measure density, is take the mass of an object, divide by its volume to get the density. And a density that you should be familiar with is water's density, which at room temperature, pure water has a density of about 1.0 grams per milliliter. And that's a common unit used to describe an object's density, grams per milliliter. Sometimes you'll see it grams per cubic centimeter, because 1 milliliter, that's the same thing as 1 cubic centimeter. So in laboratory activity 3, you're going to observe matter and distinguish between mass and weight, and then we'll do an experiment that follows a scientific method to determine the density of wood. First, let's start by understanding the difference between mass and weight. In order to determine an object's density, we need to know its mass and its volume. But we measure the mass indirectly. When you put something on a balance, what you're really doing is you're observing the effect of gravity on that mass. And so to understand better the effects of gravity on mass, we will simulate an experiment by Michael Faraday. He performed this for some of his young students back in the 1800s. Michael Faraday was a humble Christian man, but he's also considered one of the greatest experimental scientists of all times. And so take a look at your materials here. You need a digital balance, an Erlenmeyer flask, a graduated cylinder, a weighing dish, a balloon, spatula, vinegar, baking soda, and some safety glasses. Anytime you're working with potentially hazardous chemicals, vinegar, if that gets in your eye, that would be very painful, so you should wear some safety glasses. And also you're working with glass here with the Erlenmeyer flask. Now, Michael Faraday, what he did to help his students understand mass was that he took some marble chips, and marble is basically calcium carbonate, and mixed that with some sulfuric acid, and the bubbles that were produced were carbon dioxide, and then he weighed this carbon dioxide. Now, sulfuric acid is a little bit dangerous to work with, so we're going to do something similar. We're going to use vinegar and baking soda, and the first thing you want to do is get your digital balance and take a balloon, set that balloon on your balance, and zero it out. We're going to add some baking soda to an Erlenmeyer flask. That's what this conical shaped flask is here. And then we'll mix some vinegar in with that baking soda, and you can see what happens here. You can see those bubbles that are forming. That's carbon dioxide gas. The vinegar and baking soda are reacting with each other, forming carbon dioxide. Baking soda is something called sodium bicarbonate. Na is sodium. The bicarbonate is HCO3. So if you're doing this experiment at home, get 10 grams of baking soda. Pour that into the Erlenmeyer flask. Then use your graduated cylinder and get about 50 milliliters of vinegar. And anytime you read a graduated cylinder, read it at eye level. Get your eye at the same level as the liquid level. And you can see here, that's where the liquid level is, right there. And I have a little bit more than 50, but that's okay. We're just using this vinegar to try to make carbon dioxide. So get ready with the balloon, and you'll want to put it on immediately after you put the vinegar in with the baking soda, and it's going to fizz up. It's probably going to fizz over if you have a 250 milliliter Erlenmeyer flask and you do it like I did. The carbon dioxide is going to fizz up, and it may even spill out and over the outside of the Erlenmeyer flask before you get the balloon on, but that's okay. However, you may want to do this experiment like inside some kind of shallow pan, just to prevent any spills on your table. So get that balloon on as quick as you can, and it will start filling up with gas. And this is a smaller Erlenmeyer flask in this picture. It's better to use the large one because you are able to collect more gas. So mix the vinegar and baking soda, put the balloon on, and then you can pick it up and swirl it around, and it should keep reacting some, especially if that baking soda was in a big clump. If you swirl it around, it'll mix in with that vinegar better and create more gas. And when it seems like the reaction is finished, then go ahead and take the balloon off and tie it off and weigh it. And look at this, the mass of the balloon increased. Now remember, we can't measure mass directly. We have to measure weight of something. And so we lay that balloon on the balance, and it pushes down on the balance because it's being attracted to the Earth. Now if we took this digital balance to the moon and weighed this balloon again, it would weigh quite a bit less, because the gravitational attraction on the moon is less than on the Earth. However, we'd still have the same amount of gas in the balloon, so its mass didn't change, just the effect of gravity on the mass did change. Or in other words, its weight changed. So that's the main difference between mass and weight, is that weight is the effect of gravity on a mass. Now, one thing Michael Faraday was wanting to help his students understand is that all matter is affected by gravity. It's one thing to go outside and pick up a rock and notice that it drops and falls to the earth. Those are fairly easy observations to make. But what about gases, things we can't see? I mean, air is a gas, and we can feel it move by us when a fan blows or we stick our hand out the window of a car. But even things like that, like gases, those are attracted to the earth. They are affected by the Earth's gravitational pull, and that's why we can weigh them as well. Okay, we'll go ahead and pause the lesson and answer your questions here. Okay, so when the acid was added to the soda, a gas was formed. And we could tell that by the bubbles that formed and the fizzing that was taking place. And carbon dioxide, that was the substance that filled the balloon. And we know that matter went into the balloon because its mass and volume changed. We could see a volume change in the balloon, and we saw that its mass changed too when we put it on the balance. And since matter is anything that takes up space and has mass, since this changed, we know that matter went in. Even though we can't see it, we know it's there. And then the difference between mass and weight, the main way to think about that is that weight is the effect of gravity on mass. Okay, well, let's go on to part 2 now on the density of wood. And something you're probably familiar with regarding wood is that it floats when it's placed in water. And so thinking about what we just talked about, dealing with gravity, if an object is less dense than water, that's why it floats in water. And the reason for that is because for a given volume, it has less mass, which means gravity affects it less. If an object is more dense than water, then for a given volume, gravity attracts it more when compared to the same volume of water, and it sinks when it's placed in water. So in part 2 of this laboratory activity, we're going to answer this question: what is the density of wood? So for your hypothesis, go ahead and research wood's density and come up with an acceptable range of values. There are many different types of wood, so see if you can find some different densities for different types of wood. Pick the highest and the lowest from those numbers, and that will be your range of density. So we'll calculate the density of wood here, or if you're doing this at home, on your piece of wood, and if your density is within the range that you observed, then you can say your hypothesis is correct. Well, you may have been able to find that information in your textbook or on the internet. I found it in this pocket reference booklet by Thomas J. Glover, and for white pine it showed a density of 0.42 grams per milliliter, and for live oak 0.95 grams per milliliter. And just something to think about here, you may have seen something called the specific gravity for an object, and what that is the ratio of the object's density to the density of water. And so that usually doesn't have units because it's density over density, but water's density is 1 gram per milliliter anyway. And if you want units of grams per milliliter, then whatever the specific gravity is that you see, just add those units on, and that will be the object's density in grams per milliliter. If you didn't have specific gravity, just try to convert your units to grams per milliliter. Okay, well, let's look at the materials and procedure here and look at some things you need to record: the mass of the block, and then we're going to find the volume of the block 2 different ways, just by geometry. The block I'm using is rectangular in shape, so we can do the length times the width times the height to find its volume. And then we can also use something called the water displacement method, which you learned about in your lecture. Take the initial volume and the final volume after the object is added, take the difference in those to get the volume. And so we can calculate the density 2 different ways: the mass divided by the geometry volume, and then the mass divided by the water displacement volume. Now, of course, volume 1 and volume 2 should be about the same. But if they're not, we can consider that as a source of error in our experiment. Okay, let's go ahead and start by measuring the mass of the wooden block. And if you're doing this at home, you need a wooden block that will fit inside the 100 ml graduated cylinder. And you don't want it any longer than maybe 1/3 of the length of the graduated cylinder. So here's the wooden block I'm using, and it weighs 7.65 grams, so record that. Next, we need to measure its volume, and this is a device called a caliper. It allows you to measure a little more accurately than just using a regular ruler. And so you can see here I'm measuring the length right now, and I've put that wooden block inside the caliper and closed the caliper around it. And what you want to do is look at this 0 mark right here, where that lines up with this ruler. And this is like a millimeter increment ruler. And you can use the top mark too. That's in inches. But ultimately we want centimeters, because we're going to have centimeter times centimeter times centimeter is cubic centimeters. And we know that 1 milliliter is the same thing as a cubic centimeter. So we can easily convert to milliliters if we use centimeters. So try not to get confused here. We'll measure the length in millimeters, then divide that by 10 to get it in centimeters, and record that. And so we can see here that we have right beneath 80 millimeters, right around 79 millimeters, which would be 7.9 centimeters. But we can be a little more accurate than just saying 7.9. Let me zoom in on that 0 mark there, and you can see that it's a little bit to the right of 79. And so what we do is we just start looking at these tick marks, and we find the one that lines up directly with a mark above it. And it looks like to me about right, maybe this one lines up the best. Either that one or this one. So we can say 79.35 or 79.40. Whichever one you think it is. I'll remove my marks off of there so you can see it. And you make a decision as to what you think the length is. So don't forget to divide the millimeters by 10 though to convert it to centimeters. So here's the width. Go ahead and measure that. And it looks like the 0 lines up right with that mark right there, so we don't have to do any other measurements with the caliper to estimate a decimal place. And then here's the height. Go ahead and measure that. And notice here, just so you can see, here's where it says 0.05 millimeter. That's what these tick marks or graduation marks, those are 0.05 millimeters apart. So make a measurement of the height and record that. Then you can calculate your volume. Okay, now let's use the water displacement method to calculate the volume. And here you can see I have a graduated cylinder filled up and has some water in it right around the 50 milliliter mark, between 50 and 51. I'll let you estimate a decimal place there. So between 50 and 51 is where that water level is, and you can just read that line right there. That's the water level. So estimate a decimal place. Is it 50.1, 0.3? What do you think that is? And record that result. Next, you add the wooden block, and the best thing to do is to tilt the graduated cylinder to one side or the other. Don't just drop that block in there. It could splash water, and then you'll lose water and get an inaccurate volume measurement. And notice what's happening here. This wood is floating. So the only volume that we're measuring right now is this half, basically, of that block. So to get an accurate volume measurement, we need to submerge the entire wooden block under the water. And you can use a pencil, the end of a spoon, or a knife to do that. You don't want to put your finger down in there and submerge it, because your finger has a lot of volume, and that can give you an error as well. So use something that's not going to displace much water and give you much of an error when you submerge the block. Okay, so I've submerged that block, and maybe you can see that spatula running right through there, a little metal spatula that I'm pushing down with. And let me zoom in on that, and you can measure that final volume. Observe that. Record your result. Take the difference in this number and the initial volume before the block was added. Subtract those two, and that's your volume for the wooden block using the water displacement method. Okay, so you should have all the data that you need there, and then you can go ahead and do your results and discussion. And here's the numbers that I came up with, and here's my volume 1 using geometry, length times width times height. And you can round to 1, 2, or 3 decimal places. It's not that important. And then here's what I had using the water displacement method. Your numbers should be similar to mine. They don't have to be exact, but within a few decimal places of what I have. So go ahead and pause the lesson and complete the results and discussion. Do your own work. Okay, so to figure out the densities, D1 and D2, you just take the mass divided by volume 1, 7.65 divided by 17.68 for my results, and I came up with a density of 0.433 grams per milliliter. Remember, the density of water is 1 gram per milliliter. So if something floats in water, it should have a density less than water. And so that makes sense that we get a small number less than 1 here. And then D2, 7.65 divided by 15.5 is 0.494. And then the average is 0.464. Now, something to notice here on these two volumes, they're quite a bit different, a little over 2 milliliters apart. And it's hard to know which one of those is more accurate. Probably volume 2, the water displacement volume, because there were some imperfections on that wood that when measuring its length times width times height, that's assuming that it's a perfect rectangle, but it wasn't. The corners were a little bit rounded, things like that. So it definitely had less volume than 17.68 just by observing it. So 15.5 is probably a more accurate volume for the particular wooden block that I used. And then I had a question here to answer. Is helium's ability to rise in air caused because it is unaffected by gravity or because it's less dense than air? Well, it's because it's less dense than air. And what I was hoping you would do is connect what we talked about in part 1, that everything is attracted by gravity. So why is it if you have a helium balloon and you let it goes away from the Earth? Well, the reason is because it's less dense than air. Just like wood floats on water, and if you took a piece of wood and dove underwater and let it go, it would rise to the top. That's the same thing that happens with helium in air. You let it go, it rises up. So helium and all matter is affected by the Earth's gravitational pull, or anything's gravitational pull for that matter. Okay, let's look at the discussion. Was your hypothesis correct? Yes, the density was within the range of values for wood. I was kind of on the low end of the range that I had, but it was within the range. And then some sources of error here include inaccurate volume measurements, instrument error, and then errors in calculating volumes and densities. So those differences we had in our geometry and water displacement methods for figuring out the volume, there's obviously some inaccuracies there because of the differences that we obtained. And then part 3, some similar questions that could be answered by conducting a science experiment. What is the density of fill in the blank? Lead, iron, etc. And then how does temperature affect density? Does that affect the density of a solid, a liquid, a gas? Does a change in temperature affect the density of any of those phases? Okay, well that's all for laboratory activity 3.